The next speaker is Kate Willett, who is a graduate of the School of Environmental Sciences here at UEA and is one of those 74 people who did their PhDs in CRU. Kate produced a global data set of surface humidity, a tricky variable to work with, and showed that humidity had increased mainly because of human-induced change. Since 2007, Kate has been climate scientist at the Met Office, and today she'll be talking about observing our changing climate with surface humidity, an awkward but essential climate variable. Kate, please.
Expanding this slide set. Can you see that now? I'll assume that's a yes. So thank you very, very much for inviting me to speak. CRU is always a place that's very dear to my heart after spending many months battling with my PhD down in the CRU basement. So it's a real pleasure to come here today and talk to you about my work on surface humidity and climate change and why I think surface humidity is such an important variable, but really quite a problematic variable to work with. So I thought I'd start with my kind of take-home message, so it doesn't matter too much if you drift off in the next 20 minutes. And so the headline really is that surface humidity has changed since records began in 1973. And of course, we had data before 1973, but it's really only at that point that we had enough to undertake a global analysis. So if we start over here on the left, these are decadal trends of specific humidity and relative humidity. So if we look at the top map, this shows us that the amount of water vapor in the air at the surface, the specific humidity, has actually increased over time since the 1970s, almost everywhere where we have observations. But at the same time, the air has actually become less saturated. So if we move down to this lower map, there's lots of brown boxes which show you that the relative humidity has actually decreased over that same period. If we move on to the middle panel, this shows us the global average time series in various humidity parameters. So this one here, D, is showing the specific humidity. And you can see that overall the long-term trend is clear, and you can see the same for the relative humidity in panel F down here, that the long-term decline is clear. But what we can also see is that there's lots of strong year-to-year variability, and this is associated with things like the El Nino and La Nina, and also some very interesting decadal variability, which I'll get onto a bit later. Finally, on the right, this is a seasonal analysis of the Northern Hemisphere land. And here we can see that the specific humidity and the temperature are very strongly correlated in all seasons. But that this decrease in the relative humidity is really coming from the spring, the summer and the autumn seasons, and not so much from the winter seasons. And again, I'll talk about that more. But before I go into more detail on this, I wanted to take a step back and actually give you some more background on humidity and why I think it's so important and why I think it's also very tricky. So there are many different ways to quantify surface humidity. Firstly, we've got the absolute measures. This is the amount of water vapor in the air. I've already talked about the specific humidity, and this is the one that I use the most. And this is the ratio of the mass of water vapor to the mass of moist air, and we measure this in grams per kilogram. Then we've got the relative measures. So this is how close the air is to saturation. And here we've got the relative humidity, which is the amount of water vapor in the air relative to the maximum that there could be at that temperature. And then we've got thermal measures, and I've described these as the potential effective evaporative cooling of water vapor. So we've got the wet bulb temperature, which is the temperature of the air cooled to saturation by evaporation of water into it, and the dew point temperature, which is the temperature that the air needs to be cooled to in order to reach 100% RH. So these are subtly different things, and we don't need to worry too much about that at the moment, but you can see that there's lots of confusion could arise depending on which variable you choose, and knowing which one to choose for which purpose is quite difficult. And also if somebody says, well, I'm looking at humidity, it's really important to know, are you looking at the specific humidity, which is going up, or are you looking at the relative humidity, which is going down? I believe that humidity is just a really important variable for so many different reasons and across so many different sectors of society. So fundamentally, it's it's an integral part of the hydrological cycle. You've got evaporation and evapotranspiration of liquid water into the atmosphere, into a gas, into water vapor. And this then becomes a source for cloud formation, and then in turn a source for precipitation. So it's really, a fundamental part of the hydrological cycle. But then we've got the energy budget. And actually water vapor is absolutely fundamental to the Earth's energy budget. So water vapor is the most abundant greenhouse gas, and without it, we wouldn't be able to survive on this planet. If we take away all the water vapor, then the global average surface temperature would be closer to minus 18 degrees, whereas at present day it's about 14.5, 15 degrees. So as the energy comes into the Earth, and it can evaporate water, and so that means more energy is going into evaporation than sensible heating of the surface. And that evaporation is actually a cooling process. So as water is evaporated into a water vapor, that's a little bit of energy being taken away from the surface and locked up into the water vapor. So the water vapor, or the humidity, is an energy store for the atmosphere. And that can then be transported around the atmosphere vertically or horizontally. So water vapor is a key mechanism in transporting energy. And then the water vapor may eventually condense back into liquid form, and that releases this energy and can heat the surrounding air. Humidity is really important for thermal comfort. So humans and animals need to regulate their body temperature to survive. And for mammals, this depends on evaporative cooling. So for humans, we sweat, and that sweat is then evaporated away, and that helps to cool our bodies. And for animals, they pant, and this helps for them to evaporate moisture from their internal body surfaces and cool them down. But importantly, this evaporative cooling is only effective if the air is below 100% relative humidity. And the closer the air is to 100% relative humidity, the harder it is to stay cool. This wet bulb temperature that I've already mentioned actually gives us this critical level above which the human body can't survive. And this critical level is 35 degrees of wet bulb temperature. And this is because when the wet bulb temperature matches the air temperature, it means that the relative humidity is 100%, so you can't have any evaporative cooling. Now, our skin temperature is on average about 35 degrees. So if the wet bulb temperature is 35 degrees, then the air very close to our skin has 100% relative humidity, so you can't evaporate any moisture away, and the human body can't cool. So this is really quite alarming, but actually there are very few places on the globe that are even approaching a wet bulb temperature of 35 degrees at present. However, as I've shown, the water vapor of the surface atmosphere is increasing, and with that the wet bulb temperature is also increasing. There are many heat stress indices that now incorporate humidity alongside temperature and radiation and wind speeds. You've got things like the wet bulb globe temperature, which I've included a table of thresholds up here on the right, and you've got things like the Universal Thermal Comfort Index. So clearly humidity is really important for health and well-being of humans and animals. And then it's important for a whole host of other sort of day-to-day things. So, how quickly is your washing going to dry? How likely is it that ice might form? And also more recently, there's been a lot of research going into humidity and virus transmission, particularly around COVID-19. So it's a really, really important climate variable. And now I'd like to tell you a bit more background on some of this sort of the difficulties with measuring it and quantifying it. So traditionally, the humidity would be measured using a wet bulb thermometer. So this is a normal thermometer, but it's surrounded by a piece of material that's continually wetted, called a wick. And what happens is the water from that material is evaporated away if the air is below 100% relative humidity, and that cools the wet bulb thermometer and gives us the wet bulb temperature. And so the difference between the wet bulb temperature and the dry bulb temperature tells us the relative humidity. More recently, we've moved to electronic sensors. So these are capacitance sensors or resistance sensors that give us the relative humidity more directly. And that's because they're easier to maintain, they're cheaper, and we can get more frequent observations from these. These instruments are housed within something called a Stevenson screen that Phil just mentioned, and this protects these instruments from direct solar heating and strong winds. And they're routinely used in weather stations over land and on ships. So if we look at this map over here on the left, you can see the coverage of observations over land. So each box is a 5 by 5 degree grid box, and the colour represents how many stations are within that grid box. So the coverage over land is actually really quite good, apart from sort of parts of Africa and South America. But it's clear that there are a lot of grid boxes that are dark red, so they only have 1 or 2 stations. And so when we're looking at much more regional detail, these grid boxes are vulnerable to data gaps and data errors. If we look at the marine data, the picture is not so good. So there's huge gaps over the Southern Ocean. And actually, when we look at the grid boxes that have a high enough density of observations for us to be confident in what they're showing us, it's only really these blue regions, and that's really the Northern Hemisphere. And even worse than that, if we look at the proportion of the globe that is covered by marine data over time, that's this blue time series up in the top right, we can see a steady decline from the late 1970s to present day. So around 1980, we had about 7,000 ships regularly reporting, and that's dropped to about 1,000 to 2,000 at present day. And it really is at critical levels where we're really now struggling to be able to observe the surface humidity over ocean. In addition to sort of some of the observational issues, we've also got changes over time that can cause issues both for humidity and for temperature. And often when we're assessing humidity, we're also using information from the temperature. So we have to deal with the uncertainties from both variables. So it's kind of double trouble, if you like. So I'll go through some of the main issues here. So we've got instrument changes, and I've already discussed this move from wet bulb thermometers to RH sensors. But within that, you might have several instrument changes over time. And observations have generally become more frequent as we move to automated sensors. So all these things can cause slight subtle changes in the time series. Stations have moved over time. So these could be big moves as a station moves from a city to an airport, or they could be small moves, just a couple of meters within a station site. But even those small moves can cause subtle changes in the mean and variability of the ambient temperature and humidity. The local environment might change. So you could have urbanization around a station, or changes in forest cover, or changes to irrigation practices, or again, small changes like adding a concrete path into your station site enclosure. And these could again change the mean and variability of your measured variables. And for ships, they have their own set of biases on top of that. So ships have got bigger over time, which means that the observation height has increased. And if we don't account for that, then you could get spurious trends in your long time series. And the ship itself is often made of metal, so this heats up during the daytime and can have daytime biases. So a lot of work goes into detecting these issues, for either adjusting for them or removing them, or if we can't do that, then building an uncertainty model to account for them. And that's what I've been doing with my work on the HAD-ISCH dataset. And so you can see that a lot of care has to go into humidity because it's such a tricky variable. And finally, I'd like to actually talk to you a little bit about surface humidity and climate change. So I'll start with a quote from the most recent IPCC. So this is the AR6, and it's from the Summary for Policymakers. And this states that it is unequivocal that human influence has warmed the atmosphere, ocean and land. Widespread and rapid changes in the atmosphere, ocean, cryosphere and biosphere have occurred. And humidity is very much part of this story of climate change. So if we look at the time series on the left, this is the global mean surface temperature. And it's very clear that this has risen over time. And so this, we know that if the air becomes warmer, then it has more energy to contain more water as a vapor. And that's exactly what we see. So if we look at the specific humidity from my data set, then this shows us that the specific humidity, or the water content of the atmosphere at the surface, has increased over time. But as I said, it's an awkward variable, and there's a lot of complexity in the detail of these changes. So I've already shown you these maps on the right. The one on the top shows us the specific humidity, and it's blue almost everywhere. So we've got increases in specific humidity over most of the globe. So the water vapor content of the air has increased, but at the same time, the air has become less saturated and the relative humidity has decreased. And so this means that although there's more water vapor in the air isn't holding as much water vapor as it could, given its temperature. If we look more at the sort of the temporal variability, I mentioned that there's some interesting stuff going on with the decadal variability in these time series. If we look at the temperature time series above, from about 1970 onwards, and this last third, it's almost linear. I think there'd be some debate about it, but practically linear. Whereas if you look at the same time series for specific humidity over the same period, it's not linear. So you've got a steady increase from the 1970s to about 1998, and then it's actually very flat for quite a long period until about 2013, when it continues to rise. And the relative humidity is the opposite. It's actually relatively flat over that early period, and then a steady decrease from that period onwards. So there's lots of complexity in this detail that we need to understand more. If we look at this seasonally, here we've got the Northern Hemisphere land and the Southern Hemisphere land. We can look at the temperature and humidity relationships. And here we see that in the Northern Hemisphere, the temperature and specific humidity are really strongly correlated over all seasons. But in the Southern Hemisphere, they're basically practically decoupled. Partly this is because we're mostly observing perhaps the drier regions of the Southern Hemisphere, and we have large data gaps. But we also see this in the reanalysis as well. If we look at the scale of the increase of specific humidity with temperature, and this also tells us about this relative humidity decrease, we see that the decrease in relative humidity is really coming from the springtime, the summer and the autumn in both hemispheres, but that the winter is much closer to constant relative humidity. So you may be saying, well, this is all one data set, so how confident are we in what we're seeing? And so I'd like to show you some supporting evidence from other data sets. And this is some work that I do annually for the BAM State of the Climate report, where I lead the surface humidity section. So on this left-hand panel, you've got the specific humidity and relative humidity from HAD-ISCH, and in the right-hand side, you've got similar estimates from the reanalyses. And if we take the top two lines, that's the specific humidity over land and oceans, you see that the wiggles are practically the same, and they're telling us the same story of long-term increases in specific humidity. And rather nicely, this is backed up when we look at different variables such as the total column water vapor. So we see similar wiggles and a similar long-term trend. And we would expect to see this because most of the water vapor in the atmosphere is at the surface. So the total column water vapor should look very similar to the surface-specific humidity. So that's sort of more confidence in what we're seeing in HAD-ISCH. But if we look at the bottom two panels over here on the left, this is the relative humidity. So we can see the relative humidity over land in this line, a good agreement between HAD-ISCH on the left and the reanalyses over right on the right. And so we're pretty confident in this decrease in relative humidity over land. But if we go to the relative humidity over ocean on this lower panel, this is a really interesting story that's emerging, and one where there's a great degree of uncertainty, and I'll talk more about this later. But what we see is a small decrease in relative humidity over oceans from HAD-ISCH, and a small decrease in relative humidity over oceans from the reanalyses. And what's particularly interesting here is that ERA5 is actually independent from HAD-ISCH. ERA5 does not assimilate surface humidity observations over the ocean. It does over the land, but not over the ocean. But we're still seeing a decrease in relative humidity, although the temporal variability is quite different. And as I said, I'll talk a bit more about this a bit later on. So if we go back to relative humidity over land, this is really quite a robust feature and one that's better understood. I've just had a PhD student look at this, and she was looking for what would be the drivers of relative humidity over land, and she's just passed her Viva, which is great, so hopefully we'll get some papers out on this soon. But the biggest driver of this decrease in relative humidity over land is really the fact that the land is warming faster than the oceans. So much of the water vapor in the air over land comes from advection of moist air that's water evaporated over the oceans. But if the oceans are warming more slowly, then there isn't enough evaporation or water vapor content in that air to keep relative humidity constant when it's advected over land. There's been a few papers on this. So Robin Chadwick led a paper that I was a co-author on, and then there's been papers by Michael Byrne and Paul O'Gorman, and they've devised simple models to predict the changes in specific humidity over land based on the change in specific humidity over ocean and the climatology over land. And this produces a pretty similar spatial patterns to what we see in the observations, but the magnitude of relative humidity decrease is much smaller. And so there are obviously other drivers at play. And so my PhD student was looking at dynamical drivers, and here we mean changes to circulation, so changes to pressure patterns of wind speeds, and changes to modes of variability, such as the El Niño Southern Oscillation. And she was looking for large-scale relationships between the changes to these and decreasing relative humidity. She didn't find any large-scale relationships, but she did find significant correlations at the small regional scale and for seasonal timescales. She then looked at terrestrial drivers, and here she looked at changes in land cover and land use. So this is things like tree cover, irrigation, urbanization. And she also looked at stomatal conductance efficiency. So this is where, because we've got higher levels of carbon dioxide in the atmosphere, plants can actually be a bit more efficient. So they don't need to open their stomata quite as widely, which means that there's less water loss through transpiration out through their stomata, so less water vapor coming from the plants. And again, she found significant relationships at the small scale, seasonal scales and small regional scales, but nothing that was kind of large scale. So there's definitely more work to be done here in terms of trying to quantify the magnitude of these drivers and sort of where they're most effective. I think a really important part of this story is what about the climate models? So to what extent can these reproduce the decrease in relative humidity over land and also replicate the mechanisms that we think might be going on? And here I'm showing some work that was led by Robert Dunn, of which I was a co-author on, and he looked at the CMIP5 model archive, and he showed that if we looked at the whole period, the level of moistening and warming in the historical runs was actually quite comparable to HAD-SCH. And for some models, they did show a small decrease in relative humidity. But when we looked at this later period, so in this study, it was 1995 to 2015, the models couldn't replicate anything anywhere near the rate of decrease in relative humidity that we see in the observations. And so if that observational decrease continues at the same rate, and indeed since this study it has continued to decrease and it doesn't appear to be abating anytime soon, then that does bring in an extra level of uncertainty in any kind of climate impact based on projections of the hydrological cycle. It doesn't mean they're wrong, it just means there's an extra level of uncertainty to be taken into account. We know that some of these regional decreases in RH can be linked to changes in modes of variability in circulation or changes in land use and land cover. And these are things that we wouldn't expect the models to be able to reproduce that well. So it's not perhaps a very fair test. We also know that the changes in humidity over land depend on the climatology in the first place of the humidity over land. And again, the Dunn et al. Paper shows that the CMIP5 models overestimate the relative humidity in the mid-latitude and high latitudes, but they underestimate the relative humidity in the tropics. So that could be a factor. But really, I need to do some work on CMIP6 to see if this is the same story. And a recent paper that's just been accepted by Richard Allen, again, I was a co-author on, just urges caution in the observations, and I still think there are some observational issues that might need to be unpicked. We're still confident in this decrease in RH, but the magnitude of it might be slightly uncertain. And finally, I said I would come back to the relative humidity over oceans, because I think it's a really interesting story. So the climate models tell us that really with climate change, there should be no change in relative humidity over the ocean's surface, or if anything, a small increase. But what we see in the observations is a small decrease in relative humidity. And we see this in HAD-SCH, and we see this in the reanalyses. And we know that ERA5 is independent of HAD-SCH because it doesn't assimilate surface humidity observations over the ocean. So the fact that the reanalyses have a very different temporal pattern to HAD-SCH rings some alarm bells. So there is obviously some uncertainty here, although the coverage is very, very different because the reanalyses have complete global coverage. But then we know that the observations for HAD-SCH are also very limited. This map on the right, top right, shows you the grid boxes for which we have continuous coverage over the HAD-SCH record, and there are very few grid boxes over the oceans. So there's definitely a big question mark over observational biases and errors. But if this is a robust feature, then we need to think about what physical mechanisms could be driving it. And I've just put a few very ad hoc things in here that have not been studied yet, but possibility of perhaps advection of some dry air over land, there might be some changes to atmospheric circulation and wind speeds over the ocean, or changes to the relationship between sea surface temperature and marine air temperature that are probably related to circulation. But this is very much an area of uncertainty and research that needs to be done. So this is my to-do list for the next few years. I'd like to leave it there. Thank you very much for listening. I hope you agree that I think humidity is one of the most important variables. It's certainly important for a wide range of society and also physical mechanisms. But also it's one that we have to take great care over when we're working with. And I think I'd just like to highlight again that this lack of ship observations is really now very critical. And it's severely reduced our ability to understand changes in surface humidity over oceans. Thank you very much.
Thank you, Kate, and congratulations on taking on humidity. Questions for Kate? Tim.
Thanks. This issue of the marine data reductions, is it because fewer measurements have been taken or because fewer measurements have been shared?
That's a really good question. I don't fully know the answer. I suspect it's both. I think there has been some effort going into trying to encourage more ships to share their observations. And I assume that there are plenty of ships that probably don't report. So yeah, the short answer is that I don't know. Sorry.
Hello, Kate. This is back to the point I made, that the numbers of ships reporting has reduced, but also there's been a dramatic increase in the number of drifters and drifting buoys. So they don't measure humidity measurements. They don't do any human-based measurements either, like clouds and visibility. So we have much better sea surface temperature measurements now, but much worse variables for others like humidity and clouds, etc.
Thanks, Phil.
Thank you, Phil. Natasha, we have a question from online.
So we've got a question from Siddharth Sivaraj. Since you mentioned humidity and temperature are less correlated in general over the southern hemisphere, if one is to examine whether changes in humidity levels have any effects on certain heat impact, which is independent of the effects due to the dependence between temperature and humidity, would it make more sense to look at the effects in the southern hemisphere as opposed to the northern hemisphere?
Again, a good question. I think that conclusion about the humidity being less correlated in some southern hemisphere was, we were looking at quite large scale averages, and so if you look at the smaller regions, there will certainly be locations where it is still very highly correlated. So I think these things, especially when you're looking at the heat impact on people, needs to be probably looked at much more on a regional basis, and thinking about what specifically you're interested in.
Thank you very much, Kate. Thank you. Questions. I think we need to move on. Any more questions, Natasha?
Yep. So we've got one from David Parker for, I think this one was for Kate. How about subsampling ocean reanalyses to HAD ICDH coverage?
Thanks, David. Yeah, that's a good question. We have done this a little bit, and what do we see? I'm trying to think back to that research. Okay, I can't pretend to remember what happens, but that's definitely a really good plan. So I've got some time now over the next couple of years to really go into a bit more detail on what's going on in the marine surface humidity. So David, I'll get back to you.
Thank you, Kate.
There's another question for Kate as well from Charlotte Pascoe. What, if any, implications are there of the downward trend in relative humidity for extreme weather events?
Well, that's another good question. I suppose we know that there's links between the specific humidity and very heavy rainfall. So I can't answer that question precisely, but I think it's of interest. And when I hinted that there might be uncertainty in the climate model, impact model projections based around the hydrological cycle, I suppose that's what I was getting at. And I think it's something we need to understand. How much does it matter? It's small changes in relative humidity. Is that something that we need to worry about in terms of societal level impacts? And that's not something I've done research on yet.
Well, if there are no more urgent questions, I think it's time to firstly congratulate the seminar organisers from the Climatic Research Unit for putting together such a coherent programme, observations and the way in which those observations might be used, with an adequate opportunity to highlight the importance of CRU's contribution over the last 50 years. So thank you very much for that. And I'd also like to thank our 4 excellent presenters. Phil, here in the room, Kate, and Ben and Cassia online. All excellent presentations with wonderful slides. I'd like to thank you on behalf of the whole audience.